Alright guys, we're going to be doing some more IGCSE physics papers. We're going over the summer of 2014, paper 31. This is one where you would write into it. We're going to not do every single question because we've got a lot to cover, so we'll just pick out the slightly more interesting ones. So let's jump straight in. All right. Yeah, we just got the question on the thermometer. The first question is, what are the assumptions made by, if you've got these equal spacing, what are the assumptions made about the liquid? And the answer basically here is that it has sort of like a uniform expansion. In other words, when it expands from one volume to another volume at one temperature, it'll do the exact same change in volume at a, let's say, a slightly higher temperature. Another way of putting this is a sort of a linear expansion. Okay, the next question just moves, briefly talks about the scale, what would happen if you required the divisions to be larger, what you would choose to do then. There are again a whole number of things. You could either reduce the capillary size or change the type of liquid or change the size of the bowl. There is a whole range, so let's just keep moving. What would you need to do if you change the scale? It's quite obvious. If these divisions got bigger and you wanted the same temperature range at the end, you would have to lengthen the thermometer. Okay, the expansion of the liquid in the example just shows one property. Basically shows that you can measure temperature using expansion as a property, but what are the other ones you can use? It's quite simple. You can either use change in electrical properties or, for example, an expansion of a gas. There's also radiation, like the dependence of the radiation sort of emitted by a hot metal. Like, in other words, you can look at like the amplitude of the radiation released, or the frequency as another way, other properties you could use. Okay, a student has a large number of coins. So this is basically one just asking about how you would go about measuring the density of something. In this specific example, it's coins. So they just briefly ask you for the formula. This is just quite simple. You have to set sort of mass over volume. And then it sort of goes on about how you would go about this. And basically the easiest way of going about this is using a liquid to measure volume. So you have a set amount of liquid in a beaker, in a measuring cylinder, and then you chuck your coins in. You can either chuck one or you can chuck a bunch and get some sort of average. You measure the change in the volume. And once you've got the change in the volume, you just you take the mass of all the coins or of the coin, and you divide it by the change in the volume, and you should get some density. Then it asks sort of like what to look out for, what precautions can you take, and it's just sort of all about like how you go about taking the measurements. One of the things is to remember about the meniscus, and not to you always use the bottom of the meniscus when you take your measurements. Try and make sure that your eye is nice and level with it, so you don't get any errors. I think they're called parallax errors. Another thing is to use the right sort of sizes of cylinders. If you use really big cylinders, the change in volume would be very hard to measure, so you would get basically a less sensitive answer. All right. This is a question number 3 is to do with potential energy. So you just need to basically plug in your potential energy formulas. So the first part of it is calculate the power used in raising the water. So we've got the mass per minute, and we've got the height. So we just use mgh. Okay, we can use a value for g as around 10, or if you want to be fancy, 9.81. You then figure out first the energy. So then you just go mgh, mass, h is 140, and as I said, g is, let's stick it at 10. So that would give us the overall energy. And then we have how much that is per minute. So then we just have to divide by 60 to get it into seconds. All right. So the efficiency, this is just using in the definition of efficiency, which is output over input. Remember, this is this is 100. So remember, you might have to divide certain numbers by 100. But again, this is quite a straightforward question. Just plug in your answers into the formula. This one's slightly interesting, and I'm not sure I'm 100% happy with the actual question itself and the answer. So it's talking about what would happen if there was a horizontal wind blowing, and explain why the water still rises to a height of 140. And I think this is an oversimplification of nature, and I probably think depending on how strong the wind is blowing, it would not at all, because I think drag is a lot more complicated than they sort of put it out in this question. But basically what they want to get across from the learner is that basically, because it's horizontal and as opposed to the vertical movement of the water, it shouldn't ultimately have an effect on the horizontal rise of it. But I don't agree with this. I think it's incorrect or a badly formulated question and far too oversimplified. Okay, so this is quite a straightforward question to do with. I mean, it looks quite intimidating with all the numbers and symbols and stuff. And basically, some weight is being held in equilibrium by two strings attached to a beam. All they want you to do is sort of redraw this diagram out, keeping the scaling, and from that you can work out the forces and the weights on the beam itself. One thing to mention is that you can do all of this without having to draw out triangles. In reality, as an engineer, we would just use trigonometry and your trig, cos, and sine functions to do all of this. It's far quicker and easier. But yeah, it's sort of reasonably straightforward question, so we'll move on. Okay, so this is to do with sort of like a water tank. So they want some very sort of straightforward calculations that you can, let's see if we can find them in the notes. There's, again, just plug and play style type question where you just chuck things in. Here, some of the answers broken down. But it's quite straightforward, so we can just move onto the more interesting one. So at the bottom here, we've got the for question B of this, we've got these two sort of tanks, and so they have different shapes, but they have the same volume and the depth of water in both tanks. So this height, these, and the same heights. So the density. So the first, they want you to calculate the density of the water and the pressure exerted by the water on the base of the two tanks. So it doesn't matter what the shape and actually the volume in that case for this, like for the water on the bottom. So in other words, this component, this little bit of pressure here, right? It's all about the column just above it. So in this case, it's this sort of whole column right above here. And in this case, it's a whole column above there. And that is just you just use your rho GH formula and you should be able to calculate it. So it's pretty straightforward. However, so then basically they take out a small but equal amount of water from both tanks. And then they want you to explain, which tank has a higher pressure on the base. And so if we go back to the formula, we can ask ourselves, well, what's creating the pressure on the base? Well, as we're saying, the density, but the liquid hasn't changed. G is obviously going to be the same because, there's no we're not talking about things in outer space here at different, vastly different altitudes. So it's about H. So which one of these tanks, when you take out a small amount of water, is going to have basically a bigger H still? And the answer is Q, because of its conical shape. If we take the same amount of sort of volume, you can see it sort of spread out more at the top. So if you take the same amount of volume, this tank is going to be less sort of sensitive to water being taken out in terms of its change in height. So if we take out the same amount of volume here, it'll be a sort of much skinnier amount, this little small change in height here versus, let's say, let me exaggerate this more, a bigger change here because of its shape. And therefore Q is going to have a higher hydrostatic pressure at the bottom of the tank. Okay, this is just some basic thermodynamics. They just want you to explain like the motion of gas inside this cylinder with a piston. And it's basically sort of random collisions bumping up against each other and bumping up against the wall and so on and so forth, sort of that random gas motion. The piston is slowly pushed down, they say, and then they say what happens to, how does it change? The temperature is staying the same. However, the volume is decreasing. So the pressure is increasing. So you basically say that there's sort of like more collisions, and there's sort of like higher rate of collisions is probably a better word. And that's sort of what is, characteristic of the increase in pressure, because these more collisions are sort of pushing up against, let's say, this piston more, the sides of the walls more, and that's sort of how you would categorize that increase in pressure. Anyway, and then they just want you to calculate the change in pressure. So you just chuck in your formulas again. So in this case, it's a PV equals a constant, and this only works because the temperature is remaining the same. You would need a different formula for the temperature. If, let's say, this was like isolated, or this process happened really quickly where the temperature doesn't have a chance to change, you would need a different formula, but this is the one you need in this context, and I think it's the only one you've probably been taught at this point. All right, this is just a comparison between trying to sort of get the student to compare boiling with evaporation. It's quite straightforward, so you can just sort of look through the answers yourself. And okay, then this is a question to do with sort of boiling a certain amount of water, and you calculate the energy converting sort of water to steam. You have a specific amount, and then you have sort of a case where you sort of a more real world case where you actually have it on a hot plate and it takes so much time, and ultimately then there's a difference between the two answers, and then you must explain why the answers are different. And it's just because one the second scenario, the sort of more real world scenario, has lots of sort of losses involved. So thermal losses to the surroundings, and just other convective losses and so on and so forth, and radiation losses. All right, this is just a question to do with basically making sure a student has sort of an intuitive idea of the sort of the magnitudes of the numbers. And so they just want the speed of sound in a gas and the speed of sound in a solid, and I think the arrows are probably like that, but around 300 meters per second in air, and around 3,000 meters per second in a solid. This is just because a solid is densely packed and can transfer the vibrations very efficiently and quickly, whereas the speed of sound in a gas is significantly slower because of its sort of compressibility, the fact that it can sort of get squished and squeezed a lot easier. Okay, and then it asks for the sort of why sound is called longitude. Well, it's described as a longitudinal wave. Basically, it just sort of the vibration or the movement in the molecules happens in the direction that the wave is propagating. So the one down here would be a transverse, but then let's say a longitudinal one, you see how the waves sort of compress and then expand and then compress, and it's sort of in the same direction that the sound is traveling. All right, next one's quite straightforward. They're just showing the displacement of air molecules at an instant of time varies with distance along the path of the. Oh, sorry. So in this case, they've mathematically visualized a longitudinal wave with a transverse movement like this. But anyway, so they're just basically then asking, what's it? Figure sound shorter. So you just need to then draw in. You need to just draw a wave that has a shorter wavelength and a greater amplitude. So if it's got a greater amplitude, then this sort of this up and down motion from sort of magnitude up here should increase to, let's say, here. I mean, they don't give any specifics, and then basically they want you to, if it's got a shorter wavelength, this needs to sort of get sort of squeezed up. Actually, I put the arrows the wrong way. So let's just sort of change that quickly. So you want to squeeze it up, and then you should get, something that's a little bit like that sort of type thing. And then if this was, let's say this is now double the frequency or half the wavelength, that would be one full cycle up till there. And this is now just a little bit extra, so we can just cross that out. And then it says, how would the sound change because of the two, because of the increased amplitude and the shorter wavelength? Basically, it would have a higher pitch for the increased, for the shorter wavelength, or higher frequency. So words can be used interchangeably. And it'll be louder because of an increased amplitude. All right, this is just chucking in your resistance equations. You just compare different calculations with two different like resistors, and then you chuck them in parallel and see, and then calculate the difference. So they're quite straightforward. So you just plug in your equations. The resistance R and the length of the wire. Okay, so now they just want you to sort of state like how the resistance of a wire change. Well, what are the relationships between the resistance of a wire and its cross-sectional area and its length? So in this case, if we keep the cross-sectional area constant and we just look at the length, then it's just sort of linearly proportional. So you can just draw a little proportional sign like that. And then for the area, it's inversely proportional. So if we keep the constant length, the resistance would be inversely proportional. So we just chuck this proportional sign and then a 1/. If you ever hear inverse, it means usually mathematically 1/. All right. And then they just wanted you to calculate the ratios. And this question sort of literally tells you what to do is plug in the resistance of these two, divide them, and just write your answer down. It's quite straightforward. All right, it's just some stuff to do with generators. And basically they're asking sort of what's sort of missing, if we're going to connect this to this. I mean, if this is rotating and this is stationary, we can even draw a little bit of a rotation thing. And what we're going to need is some sort of like slip rings. So just like, I won't be able to draw them nicely, so I'll just write it. Slip rings. All right. Okay, then it's just asking you to how the sort of current varies through through the resistor here over time. And basically it's sort of going up and down, sort of like this, sort of like a waveform because of the circular motion, the rotation. And it'll hit a peak when, these are cutting through the sort of the flux lines at a nice clean 90 degrees. So in the current part, that would be the peak out here, would be less strong if it was, in sort of, let's say, this position here. So it's a bad drawing, but you get my sort of 90 degrees to the current position. And then it just asks you how it would change if it spun faster, right? So I've sort of drawn it in dots here. It's not a very pretty drawing, but basically the frequency would increase. In other words, the wavelength would decrease. And the amplitude would increase because it's moving faster. There's more energy going in, so the amplitude would go up. Then they ask, what could you, connect between here and here to sort of get a DC current going through instead of an AC current? And you just use a rectifier or full wave rectifier. All right, so this we're just going to move past on. This is just, you just got to remember it. So it's nothing too interesting. Here again, you just need to remember how to read these things with your proton number and your nucleon number. And, know that you should minus one off the other to get the number of like neutrons and so on. So let's move straight on to the last one then. And then it talks about a radioactive sample. And it says that the counts go from this to this over a certain amount of time. And these two numbers are quite fortunate. So what you got to do is you just got to keep dividing this number by 2 until you get to that number. And once you get, to this number, you just count how many times you have to divide it by 2. So it's 3 times. So why divided by 2? Because we're trying to like figure out what the half-life is. When you ever see counts and times, it's always about the half-life of the radioactive substance. So it took 3 half-lives for over 36 hours. So it's basically has a half-life of 12 hours. So now we want to go from 600 to 150. Again, the numbers work out right. You just divide this by 2 twice. So we know that it goes through 2 half-lives, and we know that each half-life is 12 hours. So you just say 2 times 12. All right, cool. Thanks, guys. Hope this was useful, and I will see you guys soon.